Okay, this is March 8, 2022, Physics 20, Physics 38. Okay, so what we did before, we defined the electric potential energy, which the same way we defined potential energy in Physics 37. Is this integral that you see right in here. Potential energy, electric potential energy difference, right? Electric potential energy difference. That's how we define. And then we also define something else that we didn't define in mechanics. Which, by the way, is easy to define. We can do that. We can make us come up with a similar definition in mechanics. It's the electrical potential difference. It's no longer electric potential energy, but the electric potential difference. And it's very easy to... How do you define that? Let me show you how to define that. Set number in value. Okay. Is going to be the electric potential difference. Is going to be what? Is going to be, and we're going to give it a different name. It's going to, because it's a different quantity, it's going to be delta V, which is delta U divided by Q. When we divide delta U by Q, the force is also going to be divided by Q. And the definition for electrical potential difference becomes the path integral of the electric field. Okay, so that's how we defined the electric potential. Something like that can also be defined for the gravitational force and the Hooke's law as well, but we don't do that in mechanics. But it's possible to do a similar definition. Okay, so those are the important two definitions that we covered before. And we did the example for a uniform electric field last time. Okay. And for a uniform electric field, the electric potential increases linearly with x. Is a function of x. We can also come up with the potential of an electric dipole. Let's do that. Okay, so here you go. You already saw that. Did you do that? Here you go. The electric potential of a point charge. Did we do that? Let's see here. We did that, right? No, we didn't. We did the electric potential energy of a point charge. Oh yeah, here you go. We did the electric potential of a point charge. Okay, KQ over R. Okay, if the charge is negative, then the electric potential is going to be negative. But let's do that now. Let's do the electric potential of a dipole distribution. Okay? And we gotta come up with an illustration as well. Oh, PowerPoint. Let's do it again. PowerPoint right in here. Let's go for our illustration. too far ahead. Capacitor. Well, I don't have an illustration for a dipole here, but we can go to the previous one, right? That we saw for the electric field. Let's do that. We had an illustration for a dipole. Here you go. This is not a dipole yet. This is a dipole. Okay, so let's 16. I'm gonna copy this one here and paste down there where we were looking at. Just to fill the blanks. Nothing fancy. And go on to that. Here we go. Right, we have the x and y axis. We have a negative charge. We have a positive charge. Okay, so let's take a look at this example here that we have in the notes. And this one will be too much complication. Let's see here. We can along the x-axis, the y-axis. Yeah, let's go along the y-axis. We're gonna make just a frequent. Yeah, let's. Okay, so here you go. We have these two charges. We're gonna get the electric potential along the y-axis, positive and negative charge. Okay. So what we're going to do to what's going to be the electric potential of this spot is going to be the sum, the scalar sum of the contributions of the potential of those two. This guy here has an electric potential at this point y, and this other charge has a contribution to the electric potential at this point. Okay, so we're going to write down the contributions of each of dipole distribution. Let's see, separation of dipole distribution, discharge Q, and separation 2A, like that. Find the electric potential along what I call distribution instruction along the y-axis. Okay, along the y-axis. Q plus Q is at x equal to minus a and y equal to 0, and minus Q is at x equal to a and y equal to 0. Those are the coordinates. Okay, along the y-axis, right here. Oops, I shouldn't have done that. Okay, I want this one here. Okay, solution. We're going just along the y-axis, but you can go ahead do also in the two-dimensional space too, which is spelled out in my notes. So here we go. The net electric potential is going to be electric, I'm gonna put just V, okay? This is going to be V of the plus charge V of the minus charge. So let's see what's going on here. Plus charge, here you go. Okay, good. Plus V of the minus charge. That's what we call the superposition principle. Superposition principle applies both to vectors and scalars. Electric field is a vector. Electric potential is a scalar, right? That's an important difference between those two. And we gotta get here the equation for the positive charge. The electric potential for the positive charge is gonna be KQ divided. I'm gonna put it R plus, okay, the distance of the positive charge to a point along the y-axis. And then we are going to have the sum of the electric potential of the negative charge. I'm going to emphasize writing here. Oops. Negative charge minus Q. But then don't forget the distance also is going to be from the negative charge as well. Looking at the drawings, the distance to the y-axis, to the point along the y-axis is going to be what? R is a square plus y square square root. Okay, so gotta do that. Here you go. Wait, here you go. That's gonna be a square plus y square square root. Here the negative sign can go outside the parentheses to simplify our equation, and the distance is going to be the same. Okay, the distance for the negative charge here is going to be the same. It would be different if we had a point right in here or a point right in here. The square root would be different, okay? But we are doing a simpler problem. We're calculating just the electric potential along the y-axis. And can we do better than that? Well, not much better, right? All we can do here is, let's see, it cannot be 0. Wait a minute. Yeah. Yeah, it can be 0. Yeah, it can be 0, but we are going to lose the, yeah, watch out for that, okay? Watch out for that. If we do that alone, we will now find the field from the potential. Yeah. Okay, we cannot take the electric potential like that. We gotta come up with something more generic. Okay, but what you're doing, what you're obtaining here, is not incorrect. Okay, what we're obtaining here, we are getting that the electric potential is 0 along the y-axis because the distance is the same. Okay, we're getting that. So that makes sense because of what we have here. This charge is contributing a positive electric potential here, and this charge is contributing a negative electric potential here. But because their distances are the same, they end up canceling each other. Okay? Now, let's go ahead and now let's do the most generic problem. Here you go. Find the electric potential of the dipole distribution along the y-axis, right? So I'm gonna write it down. V is equal to 0, and that's correct. There's nothing wrong about that. Now we are going to do something more generic. Now find the electric potential. Find the electric potential of dipole distribution, charge anywhere in the 2D space. Okay? Okay, we still can preserve what you see right in here. And anywhere should be, I want to be consistent what I did here in my notes. Okay, let's see, minus R1. Yeah, okay. So that should be, let's okay, so let's put a point here. Okay, this point has coordinates x comma y. Oh, yeah, here you go. And I'm gonna put another one here. I'm gonna rotate that. Yeah, here you go. That's gonna be the coordinate x and y. Okay, find that out here. Find out what's the distance. This distance here I'm gonna call r plus. Here you go. Here you go. And the other one. Here you go. This distance is the r plus. Subscript. And the other one here is going to be the r minus. Okay. So how do we write down the electric potential for this case? Okay, it's going to be, let's see here, go for the plus charge. For the plus charge is going to be x uh, x minus a, right? That's this distance here. Uh, that will be x. Square plus y square, like that. Right? So let's go here. X actually is supposed to be minus a, okay? Because the x is negative. Okay, put that between parentheses. Okay, and the one and the other one will be a little bit different. It will be x minus a, like that, square. In this case, because the x is negative, let's see here. Yeah, because the x is negative, it's going to subtract from this positive a. In this case, because the x is also negative, you're going to have a negative subtracting a negative. But then you are going to square it and get a positive number. Okay, so this term here is going to be greater than this term here, just like the drawing shows. Okay, and what else do we do? Let's go the next step here. We get plus a. One term is going to be plus a. Let's see here. Okay, better. There's nothing else to do here. I'm going to erase that part. Okay, and what else can we do here? There's another way of writing that down. Okay, here I wrote that. Oh, here you go, right in here. Just like let's expand, just like I expanded here. Okay, well, it's already written down. Here you go. Don't need to do that. Already written down. Okay, and now what we can do about that? Here's the electric potential of a dipole distribution. Okay, what we can do now? We can now use the relation between the electric field and the potential to find out the electric field. The field. Let's put this way. Here you go. Find now using the above result. Find the electric field. Okay, like that. Better this way. So here you go. What's gonna be the electric field? And the electric field specifically, here you go. The electric field, the x component of the electric field. Then you can do the y component as well. Okay? The x the x component of the electric field. And that's what's going to be the x component of the electric field is going to be let's see. Yep, got it. Ex. Don't forget we have a negative sign here. And you have to take the derivative, the partial derivative with respect to x. Okay, and what we get, I'm gonna put the KQ in evidence here. That's gonna be 1 divided by that. And then we're gonna have the partial derivative on the outside. Okay, so let's do this derivative here. So I don't need that anymore. Don't need this term anymore. I'm going to start working on this one. Okay, so what we get here is, don't forget, I'm going to change the notation here in terms of powers, so it's easier to see. So it's easier to differentiate. Like that. I don't need the square root anymore. And I'm going to do the same right in here. Change the negative. Okay. And now let's do the calculation. We're going to have minus half. The power is going to change to minus 3/2. Oops. Minus 3/2 here. I don't need the 1 in there. What else do we have to do? We have to differentiate this term, right? It's going to become 2x plus a. And something else similar happens to the next term, but with a exchanged sign. Exchanged sign here. Since we have minus minus, let's put the parentheses as well. Okay. We don't need the partial derivative anymore because we did the derivative. We can cancel this guy out here. The 2 cancel out with the 2. The 2 cancel out with the 2. The minus cancel out with the minus. Becomes plus. Okay, and I'm gonna commute this term here. And that's our electric field. Oh, I don't need this partial derivative anymore. Okay. something like that. That's the y. That's the y equal the x component. Okay, that's the generic solution right in here. This one. Okay, along the y-axis. Okay, x is equal to 0, and the x component of the field becomes x component, and the above x component becomes this one disappear, this one disappears. Okay, and what else can we do? Okay, this half cancel out this other half, right? So we get third power. Here we have something similar, but with the sign exchanged. Are you recognizing that? Right? We get exactly what we expected to get, right? This term cancel out with this term cancel out with this term, like that. Okay, Ax above, along the y-axis. Yeah, I was supposed to have a Ax. Why did I put along? Okay, along the y-axis. Oh, yeah, it's along the y-axis, right? Is x is equal to 0. Sorry, gotta fix that. X is equal to 0, not y. Along the y-axis, x here is equal to 0. Let's fix that. Along the y-axis, x is equal to 0. So this one becomes 0. This one becomes 0. This one becomes 0. And this one becomes 0. Okay. So what else can we do? Okay, we end up with minus a here, right? This one becomes a square. This one becomes a square. Okay. Yeah, that's the right solution. Let's go back here to my let's see if we can, yeah, we can do more, right? So let's see here. Yeah, those two denominators are the same. Yeah, they are the same. So one more step. We are going to end up with 2a. 2akq. Negative sign. Okay. Like that. Let's put it nicely here. And go. Yeah, 2akq. Okay, can we compare that with what we got before? see. We can do along the x-axis as well if you want, okay? So let's stop here. And then you can do for the y component as well. Okay? When we make it along the y-axis, the y component is 0. Becomes 0, okay? And along the x-axis, the y component is also 0. So that's one way of finding the electric field. We find the electric field by, two ways, right? Two ways of finding the electric field. One using the Coulomb's law, the electric field, find the electric field of a dipole distribution of charge, of a dipole charge distribution. One uses the Coulomb's law for the electric field. The other using the Coulomb's law, Coulomb's law for the electric potential, and then taking the derivative of the electric potential. Okay, this result here should match the result that we got previously when we were calculating the electric field along the y-axis. Okay, so let's take a look here at our notes or schedule. So here goes spreadsheet correction. Today is the 8th. What's going on here? Huh. Something went wrong here. No, what the heck? Okay, that's the wrong one. Let me get another one. Syllabus. Syllabus is spring P37. I want the P38. Okay. Okay, that's the right one. Okay, electric potential. Today is the 8th. We're going to cover resistance, and we're going to, we're still on time, right? Electric potential. And we are going to cover resistance measurement in the lab today. Okay, what time is that? 5:30. So we're in good shape here. And let's see. Let's take a look at another problem. Another example. Let me close this guy. I don't need it. Okay. Okay, yeah, now we're gonna do a potential for continuous distribution of charges. Just like we did the electric field for continuous distribution of charge. Okay? So how do we do that? Okay, we do exactly what we did for the electric field. We considered an infinitesimal charge distribution, but instead of taking the electric field of infinitesimal charge distribution, we take the electric potential of infinitesimal charge distribution. Okay, so here you go, what we have we're doing for a ring. Let's do that for a ring. Take the contribution for the electric potential for each infinitesimal charge along this ring. Okay? And then you sum. By summing, we mean we integrate. Okay? So what we did so far, we did the electric potential for point charges. Now we're going to find the electric potential of a distribution, of a continuous distribution of charges. How do we do that? Okay. Consider an infinitesimal charge distribution. Consider the electric potential or infinitesimal charge distribution as being equal. That's why it's important to know the electric potential of a point charge, right? Let me get here. I use this one here, right in here. So when we know the electric potential of a point charge, we can extend it for different charge configurations. The electric potential of an infinitesimal charge distribution is going to be the electric potential of a point charge. And the dq is the infinitesimal charge distribution. And then we have to add the contribution of every infinitesimal charge distribution in the continuous distribution of charges. Okay, that's what you have to do. Let's take a look at the ring, a charged ring. Find the electric potential of a charged ring along the axis of the ring. Okay. So we go. See if I have it. I don't have, unfortunately, but I will have to copy from the previous one. Let me copy from. The drawings are the same, but we are calculating a different distribution. Okay, so I guess it starts here. 105. Yeah, like that. I'm going to copy all the stuff because it all applies to the electric potential as well, right? So here we go. Okay, I'll paste it right in here. Oh, what the heck is going on here? Something went wrong here. Madly wrong. Yep. Huh. Interesting. You didn't copy my stuff. Okay, let's try it again. 105. Okay. Yeah, 105. Here we go. Okay, let's try to copy again. Let's see if you copy it now. Copy it. Yeah, okay. Right here. Let's try to copy. Let's try to paste it again. Paste, paste, paste. Yeah, now it went through. Good. For some reason it didn't go through before. Okay, so here you go. We have a distribution of charges, a continuous distribution of electric charges, and I want to calculate the electric potential here at this spot. Okay, so here you go. This little charge contributes an amount of electric potential that I call V1. It's a scalar, so I don't need to put an arrow there. Okay, and this charge is at distance R1. This infinitesimal charge is at distance R1. The next one contributes another electric potential V2. Again, I don't need a narrow that because it's not a vector, right? Distance R2 and so on. Go. This V1 is this one right in here. V2 is this one right in here. But the distance is different, right? And so on. Right? Go. That's the idea that you must have. Okay, and next one is V3. I put it a color contribution V3. And so on. It's just a sum of those at this point. I don't need that anymore. I can erase it. It's the same drawing, but with a different quantity. We're going to do the case of a ring distribution of a radius r, net charge q. Okay, that's what we have to write that down. We go for find the potential of a charged ring of net charge q and radius r along the axis of the ring. That's the simplest problem we're gonna find out there, other than the point charge. The next simplest problem, right? So I want to find out the electric potential at this spot on the x-axis. That is this contribution to the electric potential dV. There is this contribution dV to the electric potential. Because it is not a vector, we do not need, let's see, we do not need the vector there. Okay, and I'm gonna put that dv1, right? Let's call that dv1. Now let's simplify the notation. Let's simplify them. Then we have the contribution of this other one. Notice that because we're not dealing with vectors, it's much easier. It's going to be much easier to solve the problem. And we don't have to worry about that component, that whether it cancels out or not. Okay, one is dv. Let's see, this one, and then we're gonna have another one. The other one, the contribution of the other one is gonna be like dv prime, right? Just to differentiate from the other one. dv prime, and so on, right? And then we have those as well. Let me erase this one here. Contributions of those. dv. I can erase that. Can erase that. Okay. I don't need this guy. What time is that? 5:43. That we're not gonna have a net field because it's an electric potential. Okay. Everybody is equidistant, right? So solution. Ooh. Oh. Huh. Okay. Solution. The everybody's equidistant, so this r here is gonna be what? This r here is going to be square root. Good. I don't like this square root. Huh. But I'm gonna use it anyway. R squared plus x squared. Yeah, see this square root doesn't extend all the way down. Let me see if I can extend it. Yep, it does extend. Okay. And we go ahead. We integrate that. Right? V. We can apply the integral right in here. And I'm gonna put it apply over the charge distribution Q. As we integrate this term, the x, this term here doesn't change. So we can be taking, because of that, we can be taking out of the integral, right? As we integrate through every element, let's see if I have it here. Every element here scans through every element in this ring, the distance doesn't change. So this distance, because of that, this distance can be, this value, this square root can be taken outside the integral. Okay. Integrate over all the q, we get kq over this square root. Let's take a look at my notes. KQ, right? That's what we end up getting. Then we can do that approximation for x much greater than radius, than the size of the ring. If you do that, this term is going to go to 0 and you get kq over x, which is the point charge, the electric potential of a point charge, okay? And we can also find the electric field of this distribution by differentiating it with respect to x. When we do that, we get the same result that we got initially for the electric field of the ring. Okay, see, let's write it down here. I want to write something at least. Okay, here you go. Making x much greater than r, comma, reduces our problem to that of a point charge. Okay. Differentiating the above with respect to x. Okay, the above with respect to x results in the electric field that we calculated before using the Coulomb's law. Okay, so that's what we have for this problem. I'm gonna go into the taking attendance right now. Let me see if we have anything else here. Searching for road that require an approximation. Yeah, I'm gonna skip that. Okay, this one should be the, okay, this one is the disk. Okay, we're going to do the disk after the break, right? Let me take attendance and then we can go into the break. Okay, 7, today is the 8th. Interesting. 8, 9, 10, okay. Delete. Mario Acevedo. Let's see. Toby, are you there, Toby? No? Toby's not here. Next is Harum. Okay, Musa. Genesis Bell. Okay. Jennifer Camarillo. Nope. Robert Faust. There. Pedro Flores. Are you there, Pedro? Nope. Lawrence Flores. Okay. Alexander Garcia. Okay. Alexander Garcia. Song. There. Brian Nies. Athena. Not here. Dylan Martinez. Rafael Mercado. Alexis Nigret. Abraham Perez. Nope. Nicolas Pisano. No. Nicolas Ramon Quintana. Okay. Ali Sharabi. Okay. Kenny Villagomez. Patrick Villavazov. No. No Patrick. Nolan Williams. Let's see, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 14 here. 2, 3, 4, 5, 8, 9, 10, 11, 12, 13. We have 15 here? It was not called. Let's see. Let me see. Let's see if we have everything right here. Okay, let's go again. Mario Jimenez is not here. Toby, are you there, Toby? No? No Toby here? Jennifer? No? Pedro Flores? No Pedro Flores, right? Lawrence Flores? He's okay, so it's just you. Anybody, let's see, at least you, right? Anybody else? Now we have 14. Let me see. Good. Starting phase. Okay. And okay, now we have 14. So I'll do here. Okay. Okay. Good. It is 552. Break. Break from 553, right? To, let's see, 608. Fetch. Yeah, 608. I'm gonna pause my recording, remind me to turn it back on, okay? Recording, okay, good. So what's gonna do next? Okay, electric potential of uniformly charged disk along an axis perpendicular to the plane of the disk. Okay, so the situation is, okay, let me see if I have the disk here. Oh, here you go. Here is the disk. We'll leave this guy here for later on. It's 1, 2, 3, right? One. Okay, so okay, let's do this one. Take this one out and put elsewhere. Okay, I'll put it here. If we have time, we do that as well. Okay, so here's the disk. We want to know the electric potential here at this point. And what we do, we consider the ring as being the infinitesimal charge distribution in the disk, just like we did for the electric field. So this ring here contributes electric potential at this point. A different ring contributes another electric potential at another point. Let's see if I have a second ring here. Yeah, here you go. Here's the second ring. First ring and second ring, right? But it's not an electric field anymore. Let me take the electric field out of the equation here. I'm gonna put a dV instead. It's the same figure, almost the same figure, right? It is almost the same figure. And then the other one, okay. Yeah, I put a dV again here. So do you see the it's much simpler to work out those problems when we are calculating the electric potential, because the electric potential is a scalar quantity. We don't have to worry about directions of scalar quantities, right? So that's why it ends up being simpler. So sometimes it's better for you to solve your problem using the electric potential. It's simpler for you to solve your problem using the electric potential instead of the electric field. Okay, so here we go. And then this one I will call dV prime because it's a different infinitesimal charge contribution. Okay, this one, okay, I don't need that. Why is it? Yeah, I don't need that. Okay, so now let's go ahead and write down our solution. Find the electric potential of a charged disk along its axis. charged disk of radius r and charge q along its axis. Solution: use the ring as the infinitesimal charge distribution, and use, let me see, several rings of different radii, right? Radii as the infinitesimal charge distribution of the disk. Okay? So here you go. The dV of the disk now is going to be given by the V of the ring, of the charged ring. Okay, like that, right? That's what we got for the charged ring. And now instead of r squared, I'm not gonna use r squared because r is the radius of the disk, right? So I must make a difference. I must differentiate the radius of the ring from the radius of the disk. The radius of the disk is big R. The radius of the ring, I'm going to say the generic r, lowercase r. We usually use the lowercase as the variable one. Okay, so I can say that, here you go, this little ring right here. Oh, I put r prime, right? In my notes here, I put r prime, but let's use it, not r prime, let's put it r, little r. Yep. Lowercase r. Lowercase r. Lowercase r. Lowercase r. And then I put the r. Here is going to be 2 pi lowercase r. We have another one. Oh yeah, we have another one here. Lowercase r. Lowercase r. Lowercase r. See, I have an r prime. This r prime is different, right? We have an r prime, that's the distance of the ring to the point, and we have the r, that's the radius of your infinitesimal ring. And let's see here. Yeah. Good. I got everything. And now if we want to find out the result, we have to integrate. Note C, if you're not sure whether you got the right result or not, just go ahead and do a dimensional analysis of this problem. Okay, the electric potential is supposed to be a K times electric charge divided by a distance, right? The electric field is supposed to be a K times the electric charge divided by the distance square. Okay, in this case, what we get? We get a distance square here on the inside the square root. If you take the square root of this distance square, you get the distance, right? So you have kq divided by distance. So dimensionally, at least this problem passes the test of the dimension. Okay, now here you go. I'm going to integrate this guy here. And initially, I'm going to Okay, this one, huh? Interesting. Yeah, I gotta. Well, there's nothing much I can do about that. So I thought I had. Yeah, I gotta use this one here. I gotta integrate over the charge Q of the disk. Okay, the K can be taken out of the integral. And now the R, right, depends. And then I can change the dq. I can write down the dq as being a linear charge. And what's that? Remember, the dq is, don't forget, is a disk, right? So dq over dA is going to be given. Oh, by the way, find the electric potential of a uniform charged disk. Uniform charged disk of radius r and charge q. That would be a better way of formulating the problem. Here you go. Q over pi, oh, pi r square, right? That's sigma, right? You can write it down here as being sigma. Yep, here you go. dq, you write that down as being q over pi r square times dA, like that. And then the dA, we go back to our drawing, right? What our dA can be said? Our dA can be said to be the area of this rectangle, which has a length of 2 pi r and a width of dr, just like we did for the electric field, right? Okay, okay. 2 pi r, 2 pi r dr. We can go another step. The pi cancels out with the pi. Okay, so I'm gonna put, and then we can substitute this dq right in here. What else can we do? Everything that is a constant can be taken out of the integral. And now that I change my integrating variable, we can change also the limits. 2kq over r squared. 2kq over r squared. Like that. This integral is easy to calculate, right? It's easy. This integral is easy. We can even leave this 2 here inside because it's going to help us in the calculation. Let's see here. Yeah, I put it here. Yeah, put it here. So what this integral is all about is going to be, here you go, let me erase that, is going to be r square plus x square. Don't forget your x doesn't change. Raised to the power half. To the power of half, like that. Did I forget anything? Let's see. If we take the derivative of this guy, we are gonna get a half on the front, a square root on the bottom. right? Okay, so we don't need to put the 2 here inside. Yeah, we don't need to put the 2 here inside, because then afterwards we have to take the derivative of this inside. It's going to become 2RdR. The 2 from this power cancel out with the half, right? So there's no need to put the 2 inside. We leave the 2 outside. And then we still have to apply the limits. Here you go, from 0 to big R, like that. Okay, apply the limits. Big R here. And I gotta come up with a parenthesis as well. Okay, and a second term with the second limit. It's going to be 0 here, right? I don't need the limits anymore. Here you go. Did I get it right? Yeah, it looks like I got it right. This x squared, take square root of x squared becomes x. That's what I'm getting for the electric potential of the disk. Let's see if it makes sense in terms of dimensional analysis. Yeah, what we have here is the R, right? Here you go. Units of distance and units of distance. Units of distance is square, right? Cancel it out, the distances, so you get KQ or over units of distance. So it makes sense. That makes sense. Let's see our solution here in the notes. Right here, that's the solution I got. Any difference? 2kqr square and the square root. 2kq, yep. And I have a negative there. Let's see, do I have a negative there too? Yeah, we have a negative here as well. So no problem. What else can we do? We can do this approximation, x much greater than r. When x is much greater than r, we have this type of configuration in which this disk start to appear smaller and smaller because we're moving further. It's like zooming out, right? It's like zooming out. Let's see if I can get that. Let's play a movie, right? I'm gonna play a movie here for you. So we gotta get this. We have this disk that's a little bit, oops, all right? No, let's see, I'm gonna do better than that. Do like that. Here you go. This disk here. Let us try to keep the if the distance, right, goes, if the height of the disk goes down, right? So we are zooming out. The disk was this one here first. Let me copy this one and paste here. And I'm going to remove everything that doesn't matter. Okay, so here you go. I don't need this guy anymore. And I don't need this one. Oops, I don't need this one right in here. Here you go. Like that. That's the first picture, right? Yeah, that's the second picture. Uh-huh. Let me see if I can get the R's so the drawing is complete. By zooming out. I don't need this one. I don't need this one. But this, and I need this one go to the back. Send to the back. Okay. And I don't need this guy. I don't need this guy. Can we bring it closer? Bring it closer. Huh. So here you go. This is larger, this is smaller, and we are moving away. We're zooming out from this X and Y coordinate axis as we are moving away, or as we are calculating the electric potential at distance every further away. The disk seems to become smaller and smaller. Okay. Until we get something very small. I'm going to make it a little bit thinner than that. The disk start to behave like a point charge. Here you go. Larger, 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 right? Smaller, smaller, smaller. That's the picture that you must have when we start to look at those cases in which you're making your X much greater than they are. Like that, here you go. I don't need that anymore because this one doesn't look as good as the other. Here you go. Do I have more? Yeah, I have more. Interesting. 2, 3, 4. 2, 3. Good. Let's do the math. Here you go. Let's do the math for X much greater than R. As you know, we should get the inverse of the square of the distance. Huh? Here you go. Approximation for X much greater than R. Let's see if we can do the lazy way. If we do the lazy way, what do we get? What do we get if we do the lazy way, right? Do we get if we do the lazy way? You know, the lazy way is just like making R equal to 0. Do you get a non-trivial solution? If we get a non-trivial solution, we are in good shape. If we don't get a trivial solution, if you do get a trivial solution, then we have to do something else. Okay, r much smaller than x, right? What do we get? Do we get a trivial solution or not? Here you go. Yeah, we do get a trivial solution, right? Don't forget, this is an approximation. Yeah. Actually, the approximation is here. Starts here. Here's an equal sign. We get equal to 0. Okay. Lazy way doesn't work. Does not work. For this reason, we have to use the binomial approximation. Okay, let's use the binomial approximation. And there is a little bit of trick. There's a little trick in there, right? To use the binomial approximation. What is the trick for the binomial approximation? We have to get something here inside the square root that is very small. In order to get something inside the square root that's very small, we have to put the x in evidence. Okay, we have to put the x in evidence, the x squared in evidence. Here you go. Putting the x squared in evidence, we end up with a 1 here inside. Not only the 1 inside, but also with a ratio of r squared over x squared. This ratio here is very small compared to 1. Okay? Then let's go to the next step. Let's do what's next. Okay, this is still an equality. I didn't make any approximation yet. I'm gonna take this x from inside and put it outside. Let's make sure I don't have too many parentheses there, right? So this x I'm gonna put on the front so it's clear for you all. Now that we can also factor the x outside this other parenthesis. Okay, here you go. I still didn't do the approximation. This is still, what you have here is still an exact solution. Now we can go ahead and start our approximation. Okay. It's better if it's usually better in a common place to put the ratio there after the 1. And now we can start thinking about doing the binomial approximation. Here you go. The next step is going to be an approximation because I'm going to use the binomial approximation. Go. So the approximation is going to be what? It's going to be 1 plus half of r squared over x squared. And that is the approximation. That I would say is the second order term because we have a square in there. The second order term because we have a square in there. Okay. The 1 here cancels out. And this 1 is this, and those two terms are exactly those two terms that canceled out. My zero order approximation. Okay. Now, strictly speaking, right? This thing is like equal sign because this quantity is going to be equal to this quantity. Whereas, but let's not forget, everything to the right side here is an approximation of v. So the one here cancels out with this one. Okay, here we go. Like that. And we are getting there. Oh, the r square cancels out. See that? This r square here cancels out with this r square. Uh, and then this x cancels out with this other x. Okay, kq over 2x. I'm a little bit suspicious of this 2 downstairs. I don't think it should be there. Let's see what we got in my notes. Let's see. We have a 2 here in front, huh? Yeah. Okay. Yeah. Okay, so it looks like I forgot a 2 upstairs. But is that what it is? Did I forget a 2 upstairs? Hmm. I do have a 2 here. No, but that's the... Let's see. Yeah, I do have a 2 here. Yeah, okay, so it looks like I forgot the 2 along the... oh, yeah, that's right, I forgot the 2 right here. Is this a step? See that? This is a step right here, from here to here. Okay, let's put the 2 in there. So 2kq over r squared, and that is the integral. Yeah, so let's put a 2 here. And now we are getting the approximation for the point charge. Here you go. 2, 2, 2, and 2, and 2, and 2, whoops, and 2. Imagine doing pages of derivations like that. Those are simple problems, okay? In real life, the problems are not like that. In real life, problems are far more extensive than what you see here. Okay, now we got it. Here you go. Approximation KQ, yeah, over X. Electric potential of a point charge. Point charge. What time is that? 6:42. We can go another 7 minutes, 8 minutes, right? Now let's do the other way. Let's do the other way. You are familiar with the solution already. Should be familiar with the solution already. Instead of x much greater than r, we are going to do x much less than r. Okay? This is going to be something that you got in your last lab. Okay, so here you go. The first thing that you have to ask yourself is whether you can do the lazy way or not. Okay? That's the first question you gotta ask it. A point charge. Okay. What do we get if we do the lazy way? The lazy way is x equal to 0. X equal to 0. Let's see if we get it there. This guy becomes 0. It looks like the lazy way works for that, huh? Look there. Yeah, looks like it works for that. And 2k. Wait a minute, there's something wrong here. It shouldn't be like that. Let's see. There's something wrong here. Is this 2k2 over r squared? Yeah, let's see how I did in my notes. Yeah, I didn't do for that. Let me think how to do for. Yeah, I didn't do that in my notes. Let's play a little bit more with that. Let's see. Let's see if I can get it. Doesn't look like I did that before, but much less than that, right? So let's get the. We have 6 more minutes to go. Here we go. That's gonna be the. Okay. Okay, a lazy way, we get a uniform electric potential. Oh yeah, that's right. Okay, the lazy way doesn't work. Why is that? There's a reason why the lazy way doesn't work. The result that you end up getting here, let me put that. The result that you end up getting here is not the electric potential to the right of the plate, but it's exactly the electric potential at the surface of the plate. Okay? What you see here is the electric potential at the surface of the plate. Okay? So the lazy way doesn't work. If you want to make the lazy way works, okay, the lazy way works. It seems, here you go. It looks like the lazy way works, but it doesn't. But it does not. It does not, because this result is for the electric potential at the surface of the plate. Okay? For this reason, we have to use the binomial approximation. But we are going to use the binomial approximation in a different way, right? Instead of, we are going to put the R in evidence, and we are going to get this ratio right in here. Here you go. Is the R, that's the one that's the bigger one. Okay? So here you go. X divided by R is the one that's going to be less than 1. This term that we have right in here is the one that gets out of the square root. Can we do anything else? No, we can't. We cannot put anything else there. We should preserve what we have and then do the binomial approximation. Here you go. I'm going to just commute those two terms to make it look better. Okay. Okay, like that. Okay, here you go. And we apply the binomial approximation to this term here. We have half here. Here you go. Half here. And now I use the approximation symbol. Have to be correct, right? We also, no, okay, we do not have an approximation here. That's good. Yep. Next. The R, we can expand this term. When you expand this term, this R cancels out. Okay, you go. All right, and now we have, you go, let me show you what we have. We have a solution that is linear. Let's see how I'm going to, here you go. Here's the zero order term. Here's the first order term. Here is the second order term. We do not need the second order term. Okay, we can cancel it out. And let's not forget that our electric potential that we got is a function, right? It's a linear function of x. It is at this point that we neglect this term because this x squared here is much smaller than this x. It is at this point that we neglect. So I'm going to put another approximation here. And now we have the electric potential that changes linearly with x, right? If we take the derivative of that with respect to x, we get a uniform electric field. So here we go. Let me just put this final result here. Good, better. I want to write that down. Taking the derivative of the above equation, we get a uniform electric field. So what you see here is the behavior of the infinitely large planar distribution of charges. That's what you have here, okay? If the point is very close to the plate, it is as though the plate is very large. Looks like to be very large. So any questions about that? So let me see. Pedro, are you here? Pedro Flores? No? Pedro is not here? Raise your hand. Okay, better. Okay. You came in the first half, right? In the second half. Okay. Okay, so let's meet there upstairs, and I'll be there shortly.